why do the rider's weights and positions affect the seesaw's motion? The short answer to that question is that they affect the net torque on the seesaw and therefore the seesaw's angular acceleration. In most cases, the riders of a seesaw position themselves so that the net torque on the seesaw is zero or very nearly zero. As a result, the angular acceleration of the seesaw is either zero, that is, it's coasting rotationally, or it's just got the smallest amount of angular acceleration. Well, that then requires a longer explanation. How does that come about? You put riders on the seesaw, why don't they produce enormous net torques? So, we know that if we put one rider on the seesaw, that rider's, because of the rider's weight, the rider pushes down on the seesaw over here on your left. That's at a lever arm from the pivot. It produces a torque and boom, the seesaw undergoes rapid angular acceleration such that that rider drops to the ground. But what if we put two riders on the seesaw simultaneously? And what I'm going to do is I'm going to position them very carefully. And look, the seesaw is experiencing very little angular acceleration, so the net torque on it is either zero or very near zero. How did that happen? Aren't these riders producing big torques on the seesaw? There are two of them. Glad you asked that question. Here's the story, and this is now the longer explanation to the question that prompted this video. That rider, because of the rider's weight, is pushing down on the board over here to your left. The lever arm that rider's force is using to produce a torque points toward your left. Here it is, and using the right-hand rule now, we can see the direction of the torque produced by that rider. The torque, we follow the lever arm, and I roll my finger down in the direction of the force, and my thumb is pointing toward you. That is the direction of the torque produced by this seesaw rider. Let's come over to this seesaw rider. I need my right hand again. I can't swap hands or I'll get the wrong answer. So, that rider, by virtue of his or her weight, is pushing down on the seesaw board. The lever arm with which that rider is producing a torque now points to your right. So there it goes, and now I turn my index finger in the direction of the force, and lo and behold, the torque produced by that rider is away from you. So these two torques are in opposite directions. This rider is producing a torque toward you. This rider is producing a torque away from you. When we add those two torques, and they are the two torques acting on this seesaw, they sum to zero or very nearly zero. And that's how it is that when I let go of this board and allow it to show you its angular acceleration, there's almost zero. If there is a little bit, and there is, I can adjust the distance of one of the riders from the pivot. This rider is producing a little too much torque, and now I move it toward the pivot, still a little too much torque, so I move it a little closer to the pivot, and now that rider is producing almost just the right torque. Let me move the rider in a little closer, and now this rider is producing too little torque. I have adjusted the rider's positions, that is the lever arms they're using, to show you that we can go all the way from almost perfect balance, and I'll talk about balance in a minute, with that rider dominating a little bit, to almost perfect balance with that rider dominating a little bit, and everything in between, including, in principle, perfect balance, where there's zero net torque on the seesaw. Actually, balance is an interesting concept. The balance that we talk about in the context of a seesaw and many other objects that teeter back and forth like a seesaw is a situation where gravity produces no torque on the object. So when this seesaw is balanced, it's experiencing zero torque due to gravity. I can come in and change things. I'm here very carefully adjusting positions in order to try to get this situation. This seesaw is almost perfectly balanced, meaning it's experiencing almost zero torque due to gravity. And that is the normal situation for a seesaw and riders. They like that situation because a balanced seesaw is free of torque. This assumes nothing else is exerting torques on it, and it will turn at constant angular velocity. It is an object that obeys Newton's first law of rotational motion. And it's not wobbling, it's rigid, assuming the riders don't change their positions. And therefore, in the absence of any torque, and there's no gravitational torque on a balanced seesaw, it turns at constant angular velocity. So, the reason the riders have to adjust their positions very carefully, and their weights are important as well, is because they are trying to sum their torques to zero. And how they place themselves matters. If, for example, the two riders have essentially identical weights, and these two riders do, they need to sit at equal distances from the pivot, because the torque they produce, after all, is the product of the force they exert on the seesaw times the lever arm they have to work with. There are some subtleties in here with regard to the angles involved between the lever arm and the force, but in this situation we can really ignore those. The forces and lever arms are essentially at right angles to each other, and our lives are simple. So these two identical riders, seated at identical distances from the pivot, produce identical but oppositely directed torques, and the seesaw balances. What if we have a heavier rider around, though? So instead of this rider, we bring up one, and this is made of steel. This is heavy stuff. So I'm going to put this rider in. If I put this rider out at the same distance as the rider on your right, it completely dominates, and I run the risk of tossing this rider. This is one of the flaws with seesaws, is it's easy for one of the riders to become an astronaut when a very heavy rider gets on the seesaw and does that to it. But this rider cannot sit that far out from the pivot. Too much lever arm for a large force, and therefore this rider dominates. It produces a torque that one cannot compensate for. So I have to bring the heavier rider in close. How close? Pretty close. I'm almost at balance. There we are. This is balance. All right, it's as close as I'm going to get. And again, the net torque on the seesaw is zero or pretty close to zero. And you'll notice that now the lever arm with which this rider is producing the torque is quite short, because this one weighs a lot. So big downward force, short lever arm. And that is balancing or canceling out the torque due to this one, which is in the opposite direction, but it's produced by a smaller force acting at a larger lever arm. So this is common in playing on a seesaw when you have two children of significantly different weights. They have to sit at different distances from the pivot. The heavier child sits close to produce a certain torque, and the lighter child sits far from the pivot to produce an equal amount of torque, but in the opposite direction. Well, that brings us to a question, and the question is this. Can two riders, and we can adjust their weights as you like, ever sit on the same side of the seesaw and still balance the seesaw? Two riders cannot sit on the same side of the seesaw and expect the seesaw to balance. That's because those two riders produce torques in the same direction about the pivot. Their forces are in the same direction, their lever arms are in the same direction, so their torques are in the same direction. And when you add those torques, they sum to something larger than each one individually. So you get a lot of torque on the seesaw, and it's terribly unbalanced. In order to balance the seesaw, the two riders, or however many you want to put on the seesaw, have to distribute themselves on opposite sides of the pivot so that their torques cancel one another, and eventually, if you do it all right, they sum to zero, and the seesaw is rotationally inertial. It has zero net torque on it and no angular acceleration. It coasts rotationally. There are two seemingly different ways to think about the balanced seesaw situation. The first way is the one we've been doing, where this rider produces a torque, that rider produces a torque, the two torques sum to zero, and as a result, the seesaw experiences zero torque due to gravity. It's balanced. The second way to think about this situation is in terms of a concept known as the center of gravity. Now, center of gravity is the effective location of an object's weight. I have one, you have one, these riders have one, even the seesaw board has one. This rider's center of gravity, that is where its effective weight is located, is pretty much at its center. Same with that rider. The seesaw board's center of gravity, the effective location of its weight, is at its middle, right there. And that might make you think that center of gravity, which is here, and center of mass, which is here, are the same idea. Center of mass, center of gravity, aren't they the same? They're not. They happen to coincide for all objects here near the Earth's surface. Celestial objects violate this concept for complicated reasons that I'll leave for another day. But small objects do have their centers of gravity at the same locations as their center of mass, but they're different concepts. Center of mass is the effective location of an object's mass, its natural pivot. We watched centers of mass in action when I threw various wobbling objects or sticks and so on through the air, and you'd watch the center of mass was traveling in the arc of a falling object. That's the mass moving and the inertial properties of the object in play. So center of mass is all about inertia and motion. Center of gravity is about forces, and it's forces of gravity. It's got to do with gravity. If there's no gravity around, center of gravity means nothing. So it's the effective location of an object's weight. The fact that weight is proportional to mass here near the Earth's surface means that center of gravity and center of mass share the same location. But they're different concepts. And so if you're dealing with the inertial aspects of an object, you're probably paying attention to the center of mass. If you're dealing with the gravitational or weight aspects of an object, you're probably dealing with center of gravity. So back to the situation here. We have objects with various centers of gravity, and that brings us to what observation that this entire structure, two riders and a seesaw, we can consider it as a single object. Where is its center of gravity, that composite object? And it turns out that this overall object's center of gravity is located right above that pivot. And it's being pulled straight down, like the centers of gravity are pulled straight down. They're gravity after all, right? The forces of gravity are toward the center of the Earth. It's being pulled straight down right toward the pivot, the center of rotation. And as we've seen before, forces that act toward the center of rotation produce no torque about the center of rotation. So this seesaw is balanced for in two ways you can think of it. One is in terms of the individual riders producing torques that sum to zero. The other way, which is kind of cool, is that the riders and seesaw together have a center of gravity located vertically above the pivot. And therefore, the force of gravity acting on this entire structure acts right toward the pivot and produces no torque. It's along the lever arm and produces no torque. Yeah. So Annie and Megan here are riding a real seesaw, not one of the little things I have in my lab. And they're balanced right now. Okay. Can you show us like this?
Wait, here we go.
It takes delicate adjustment, but Megan's distance is just right from the pivot. The pivot's right here. Annie's distance is just right from the pivot. They've adjusted it so the net torque on this thing is as close to zero basically as they can get it. But this is a boring way to ride seesaws if you just sit here balancing. I guess it's not too boring. It's kind of exciting trying to keep it balanced. But they can unbalance it in order to rock back and forth in one of two ways. They can either push on the ground with their feet. So Megan, why don't you push on the ground? Okay, and that extra force produces another torque which causes Annie to rotate down. Now Annie can push down on the ground and cause Megan to rotate down. So they're causing angular accelerations back and forth by exerting new torques on it. The other way they can unbalance this is by leaning. So each one of them has a center of gravity that's located somewhere sort of mid-body. But if they lean, they can shift the location of their center of gravity, and therefore exactly where they're exerting the forces on the seesaw board, and cause it again to experience a net torque so it undergoes angular acceleration. So if you both lean towards Annie, what happens?
You go down.
Annie goes down because basically the lever arm with which she's working gets longer, and the one that Megan's working with gets shorter. So the torque is this way, toward me. But now if we lean, everybody leans towards Megan. Now the lever arms get longer and shorter in the opposite direction, and the net torque is toward you. So they can rock back and forth. So this is how a seesaw works. Okay, you guys can go at it.
All right, here we go.
Either way, this is what makes seesaw fun, right? Is all the adjustments of the torque so that you undergo angular acceleration in opposite directions, back and forth.
This is so funny.
Seesaws are not the only structures in our world that need to balance. Mobile sculptures do as well. This mobile sculpture is entitled Happy Hanging Hardware, and I've built it out of a torque wrench, a ball peen hammer, and a metal file. Amazingly enough, each of these components is rotationally inertial. You don't see any of them undergoing angular acceleration after all. And that brings us to a question. For all of the components of a mobile structure to be rotationally inertial, how must those components be arranged? Each component of this mobile structure has its center of gravity at or below the point at which that component is supported. In effect, the pivot about which that component could rotate. This is actually a relatively complicated concept, though, because there are three components here which aren't the individual tools. First component, the simplest, is the file. That file has its center of gravity at or below this support point, which is the loop of string going around it. That's the pivot about which the file can rotate. And so the file has its center of gravity at or below that pivot, and therefore gravity produces no torque on the file. It's rotationally inertial. So far, so good. The ball peen hammer isn't an object by itself. It's not the component by itself. Rather, the ball peen hammer and the file together are the next component of this mobile. And that combined object, ball peen hammer and file, has its overall center of gravity at or below its support point, this loop of string. And lastly, the torque wrench and everything below it has its combined center of gravity at or below this support point, the support point that is acting on the torque wrench. So each of these components, the file and the hammer and file and the wrench, hammer, and file, each of those components has its center of gravity directly below its support, and therefore gravity, in pulling down on the center of gravity, produces no torque on that component about its pivot. It doesn't undergo any angular acceleration then due to gravity. It's balanced. And so the file is balanced, the hammer and file are balanced, the wrench, hammer, and file are balanced. The entire mobile then is balanced, and it's all rotationally inertial. So we see that objects that can rock or tip are only rotationally inertial if you balance them carefully. Sometimes that's what you want, like with a mobile. Sometimes that's almost what you want, like with a seesaw, where getting it perfectly balanced is interesting, but kind of unexciting in the long run, and you want to unbalance it a little bit to get some action happening. We'll talk more about balance in the episode on bicycles, but for now, it's clear that in the context of seesaws, balance and near balance are the name of the game.